Lastly, what we went over, oh, there, it started cutting it. Lastly, what we went over was I gave you the form for transformations, right?
Hi, Brooklyn.
Hi, Brooklyn.
Hi, Brooklyn.
You guys are so cool. Okay, so, now you have me sidetracked. Okay, last time what we did was we did a transformation form, correct? And then we went with our normal asymptote, vertical asymptote was at x equals 0, so the horizontal translation moved it. My normal horizontal asymptote was at y equals 0, so only the vertical translation moved it, correct? And then we went over if it was like x plus something or over x minus something or whatever, that we could change it into the transformation form and still give answers, correct? But what happens if it's not a number over x or x over x? What happens if it's x squared of something over? That's what we're getting into today. So we need to graph the function of y equals 3 over x plus 4. Now that actually can be written in the transformation form, can't it? The transformation form is y equals a over b x minus c plus d, right? So all we can have on the top is actually just a number. We can't have a variable. We can have a number. So if we go y equals 3 over x plus 4 plus 0, we actually have our horizontal asymptote. What's it at?
0.
Y equals 0 because it's not moved up or down, right? What's my vertical asymptote at? Close. Yep, it's -4, but it's x equals -4 because it's with an x. Yeah. So we're going to flip to the next page for a second. You're not going to flip. Yours are going to, well, you might flip if you don't have them. They're right side by side. We're going to put some rules. So how to determine the vertical asymptotes? The vertical asymptotes are based off the denominator. We agree? Okay. So the denominator is where the non-permissible values are. So the non-permissible values or values can result in a vertical asymptote. And I say can result because sometimes they're actually the point of discontinuity, which will make sense in a little bit. So the one we dealt with on the previous page was numerator was a smaller degree than the denominator, correct? So there's rules that go with horizontal asymptotes and or points of discontinuity. So for vertical, it's always just the non-permissible values. For horizontal, you have one version. The numerator degree is less than the denominator degree. So the last example was y equals what? I can't remember what was on the top. A 3? X plus 4? Okay. Whenever the degree of the numerator is smaller than the denominator, you can put a 0 at the back, and it would be in the transformed form. So when the numerator actually is a smaller degree than the denominator, you always have a horizontal asymptote at y equals 0. And the reason why is because you can get it into this form and your d value at the back would be 0. Up top up here, we're going to go through an example from yesterday where the degree of the numerator was actually the same as the denominator. So say we had y equals 2x plus 6 over 3x plus 1. So I gave this to you yesterday and asked you to convert it to transformed form, right? Into the standard form. What was our first step? Yeah. Right. So take your two separate numerators and write them separately over each denominator. So we would go 2x over 3x plus 1. And even if there's a minus sign, we'd still go plus negative, right? In this case, it's positive, so it's 6 here. Now, this is a harder one because I need it. The other one last time, it just had x plus 2 or x minus 3 on the bottoms. This one actually has 3x plus 1 on the bottom. So I need 3x plus 1 to go away. So would this work? If I times the top by 6, I could take a 2 out, and I would be left with 6x plus what? If I times it by 6, this is the question. So you actually have to make these properly. So if I times it by 6, or multiply it by 3, oh my lambda. Multiply it by 3, and I take a 2 out, correct? I multiply by 3, though, I'm going to get what? 6x. Is it going to go away, though? Okay, so if we multiply by 3 and we take a 2 out, we'll end up with the 3 part, correct? But what do we have to add to the back so that when we take... We need it to be just a plus 2. We need it to add to 1, right? You guys are stressing it. So we need to add 2 so that when we take the 2 out, we're left with x plus 1, and then we multiply by the 3.
Yeah, got it. That makes sense.
Then it'll be 3x plus 3. That's a lie. Why am I making this one so complicated?
I don't know. They're all sorted.
Why don't we pick an easier one?
Oh, I wrote
In pen? You're not coming back from this.
I know. For writing rules, it's not easy. That's not a rule. That's a question.
Okay, I'm just going to do this one because it's nicer. It's just to prove a point. It's not to make you guys die inside from the other option. Okay, so we go 3x over x plus 2. Plus 1 over x plus 2. What would we add to it? 6. And then we'd subtract 6, right? Because we'd take a 3 out, and then we'd be left with x plus 2 over x plus 2. And then plus negative 5 over x plus 2. I was trying to make it complex with putting a number in front of it, but then my brain hurts, so I'm stopping. Let's just go back to this. Because there's going to be a rule you're going to get in 3 seconds. You'll be like, why? But, okay. So it's going to cancel, and so we get 3 plus negative 5 over x plus 2. Okay? So my vertical translation is 3 up, so my horizontal asymptote would be 3 up. Instead of y equals 0, be y equals 3. We agree? Okay. The rule, if they're actually the same, instead of having to convert it, the only reason you should convert from now on is if they ask you for transformations. That's it. Because there's a rule. So if I give you this form, and I ask you for just asymptotes or domain and range, we're going to use rules. So the only time you should go from this form to this transformed form is if I ask you for transformations. That's it. So the rule number 2 is when the numerator equals the denominator. Okay, when the numerator equals the denominator, we're going to have something like this one. 3x plus 1 over x plus 2. And I just proved to you that it's a 3, correct? I was trying to do something more complex, and then it hurt, so we stopped because I'm not feeling well. So it's the exact same example. What you do when you have the numerator equals the denominator, you just take a coefficient, you take a fraction of the leading coefficients, and you're done to get your vertical asymptote. So when the numerator is the same degrees as the denominator, you take a fraction of the leading coefficients when they're the same degree. So these are both degree 1, because this is x to the 1, this is x to the 1, and then we take a fraction of their leading coefficients. So this one is going to have a horizontal asymptote. At y equals 3. So what do they do to do a little bit more of a trickery? So that's one example. If I give you this example, y equals 2 minus 4x over 3x plus 6. People will tell me it's 2 over 3, but it's not, because 2 is not a leading coefficient, right? So just don't fall to the oopsie here. It's going to be leading coefficient on the top, which is -4, and the leading coefficient on the bottom, which is 3, because the leading coefficients are the numbers that lead the equation. They're in front of the largest degree exponent. So my horizontal asymptote is at y equals -4 over 3. So if I want asymptotes, do I need to convert this? No, and the domain and range are just what those are not, right? And if I have a horizontal asymptote, I will have a vertical asymptote to go with it. If I have a vertical asymptote, I will have a horizontal asymptote to go with it. They go hand in hand, okay? So what would the vertical asymptote be for this one? How do we find the vertical asymptote? It's just the non-permissible value. That's what your denominator can't be. Right? That's what I said up here. Non-permissible values can result in a vertical asymptote. And they say can because sometimes they're a point of discontinuity. So here I'm going to go 3x plus 6 equals 0. 3x equals -6. So x equals -2. So at -2, if I plugged it into here, 3 times -2 plus 6 is 0. So that's why it can't exist, because it would make the denominator be 0. Okay? So that's rule 1. Rule 2. Rule 3. This could be numerator greater, but this could also be numerator and denominator equal. But it's going to involve an x squared. So at x squared equation is involved. If a factor cancels in the numerator and denominator, if a factor cancels in the numerator and denominator, you will get a point of discontinuity. A point of discontinuity. So, grab out an extra sheet of paper. We're going to do some practice questions for these 3. So you're going to have it right beside you. Extra sheet of paper right beside you.
For more notes.
Just practicing examples. Figuring out if we have asymptotes, vertical asymptotes, horizontal asymptotes, or points of discontinuity. We haven't went there yet. So all I said is if a factor cancels in the numerator and the denominator, we will get a point of discontinuity, which will make more sense when we start getting points of discontinuity. Some people have looked at it. So we're going to go to a separate sheet of paper after you write this down, but keep your notes right beside you so you have your rules. Because you've done one cumulative on like 4 units. That's not sufficiently a productive cumulative. Okay, so an example. Y equals x squared minus 3x over x. So for all of these, we are going to state asymptotes, points of discontinuity if they exist. Domain and range. That is what we're going to do. Yes. Discontinuity. This one for sure does. Because it has a squared and the x's will cancel. That's the key part. So we can take an x out of the top, a GCF. If I give you a trinomial, most of you will factor perfectly. If I give you this, you'll be like, I don't even. It's always GCF. If you're stuck and you're like, I can't do it, guarantee GCF. Okay, so we take out an x. And we get x minus 3 over x. Okay? Now, the moment that two factors cancel, you have a point of discontinuity. What the heck does that mean? You have a graph that's drawn and an open dot somewhere in it that does not exist. So, the x's cancel off. So we know we have a point of discontinuity. Discontinuity. Yep.
Every time.
Yep.
What if we don't spell it right?
At x equals 0. Shh. Because it's the same way we do the x normally. It's off the denominator. Patience, my dear Watson, patience. Okay, so what's left over is the line x minus 3. Do we have any denominators left? No. So this graph doesn't have a vertical asymptote. If it doesn't have a vertical asymptote, it doesn't have a horizontal asymptote. All this graph has is a point of discontinuity. A point of discontinuity at 0 and oh no. I don't know. I need a y because it's a point of discontinuity. And the moment I make you find the y, I am making you actually do a standard of excellence question. So if I ask you to find the y of the point of discontinuity, it's a standard of excellence. This is the nicest standard of excellence I feel like you could ever be asked. So I pray for it on every single diploma. Oh. That was not. There we go. All right. So, yeah.
What's another kind of standard of excellence from another?
When I made you do log base 10 of both sides, and I make you expand the 3 and the 2x by a plus sign, that's the standard of excellence. So when I give you 3 times 2 to the x plus 1 equals 7 to the x minus 1, that's a standard of excellence.
Really?
If I don't add the extra 3, and it's just like 2 to the x plus 1 equals 3 to the x minus 4, not a standard of excellence. Adding that extra 2, making sure you have that extra plus sign in there, standard of excellence. No, standard of excellence is supposed to be the harder level. 25% of your diploma. Okay. Point of the but some of this is easier, to be honest. Okay. So point of discontinuity, we have 0. How can we get a y? How can we get the y? If we plug it back into the original, we're actually going to get zeros. So that does not work. And that's where you all go plug it in. You need to plug it into the version without the x's. So I now have y equals x minus 3, right? That's the place I plug it into. I plug it into the reduced equation. Because if I plug it into the equation at the beginning, I'm going to get zeros in the denominator because that point makes a 0 in the denominator. So I have to plug it into the reduced version. So I'm going to get y equals 0 minus 3, so y equals negative 3. I just found the y of the point of discontinuity. I just did a standard of excellence question.
Wow.
So this, I pray for it. I pray for it every year. I'm like, please, give this as the standard of excellence.
Yeah, no, it'll be like Sarah has.
No. No, people just forget how to find the y. Okay, so we have 0 and negative 3. We agree? What graph we actually are going to draw is this graph. So the simplified version of the graph is always what gets drawn. And then you just have to remember to put the point of discontinuity into it. So if we went to go draw this, I'm going to have a line at y-intercept of negative 3 and 1 over 1. The diploma is 24 multiple choice, 8 numeric response, 3 written, 2 bullets each. Yep. Not even. Because giving that much, you guys don't even finish it in a lot of time. So that's Okay, so we have to plot our y-intercept, which is -3. And then we have to use our slope, up 1 over 1. Say you completely forget how to draw a linear line. Draw it in your y equals, or type it into your y equals and go second graph. Use the table of values and draw it at the very least. Up 1 over 1, up 1 over 1. I can go the opposite direction, down 1, left 1, down 1, left 1, down 1, left 1. And people will draw this for me. And then they're like, there you go, Lepp. Enjoy. And I'm like, okay, that's the line y equals x minus 3 in grade 10. But why is this in the rational unit? Because there is a point of discontinuity. So it actually is a rational with an open dot. So I need to go back in, and where it's 0 and -3, I actually don't have a closed dot. I have a open dot. So if you type the new one in, so people will go, they'll type in y equals x minus 3, and they're like, Lepp, there's a point there. I'm like, good. You did not type in the original equation. You typed in the equation that you got after you canceled crap off. Okay? So if you want to see what the actual graph looks like of the original, you type in the original. So go type in x squared minus 3x over x. Alpha y equals enter. So x squared minus 3x over x. And I press graph. And wait, I still get a line. And then you guys don't spot the open dot because if you have an older calculator, you can't see it. And if you have a new calculator, you're so zoomed out, you can't see it. So with the newer calculators, if I went, I'm just showing you, don't do this, -2, -2 is what I want for the max, -4, -1, 1. It's still super hard, but you can see there's a little tiny break in the graph. The old calculators don't even have it.
So then you just have to go from your board.
Yes. And I can go like this to check. Second graph. Look, at 0, I have an error. There's actually an open spot. Whether I can see it or not, my table of values tells me it's there. If you don't trust it, you can also go second trace value, 0, enter, and it gives you nothing because there's nothing there for a while. Okay. So, all I have is a point of discontinuity. I do not have an asymptote. People will say I have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals -3. You absolutely do not. You only have a point of discontinuity. So the moment it cancels off, it's a point of discontinuity and it cannot be anything else. You cannot name it anything else. That is what it is. Okay? So what happens if I give you a numerator that is the same? Well, we'll practice one more of these. Example. Y equals 5x squared plus 4x minus 1 over 5x minus 1. And I forgot what I was going to do on the other one. The other one I was going to do domain and range too. What's my domain? X such that cannot equal. The whole graph is there except for the 0 XER. What about my range? Y such that Y, everything's there, but what Y is not there? -3. Yeah. So the domain and range are really easy if you found the asymptotes or points of discontinuity.
Can you explain it one time more? There's no something.
What do you mean? On your calculator, because it's so tiny you can't see it, or in some instances with the TI-83s, it'll still make it close because the calculator believes that everything is continuous. And this graph isn't continuous, so it'll connect it even though it's not connected.
Yeah, you do. It's just right on the. You
It's on the y-axis.
See how it stops right before your line and right after that one?
Your calculator will actually see it. If it's not on 0, you'll be able to see it. You'll see it more on this one. So do this one. Do this one. Yeah. So we factor 5x squared plus 4x minus 1. And we say what multiplies to give us negative 5 and adds to give us positive 1. Okay. You take a 5x out and you're left with x minus 1. You take out a plus 1 and you're left with x minus 1. So it factors to 5x. Something is wrong. What did I do? Oh, it's a plus 5. Darn it. Plus 5x. I knew it needed to be 5x minus 1 so they would cancel. And then plus negative 1x. Okay. Take out a 5x, you're left with x plus 1. Take out a negative 1, there we go. X plus 1. 5x minus 1, x plus 1. And I know I needed a 5x minus 1 because I needed that to go away, right? So I get 5x minus 1, x plus 1 over 5x minus 1. Now the 5x minus 1's cancel. And I go 5x minus 1 cannot equal 0. If I want to do the non-permissible value, 5x cannot equal 1. X cannot equal 1/5. This is true. Yes? So my point of discontinuity is going to be at that value because that's where it does not exist. So the point of discontinuity is that x equals 1/5. So just like when you state vertical asymptotes and horizontal asymptotes, you say they equal that value, even though the value doesn't exist, because asymptotes are where the value doesn't exist. Point of discontinuity is where the value doesn't exist, so you put equal signs. Say non-permissible values, you'd say it doesn't. Then we reduced it, and we now have y equals x plus 1, and we're going to plug 1/5 in to get our y. So 1/5 plus 1, so y equals 1/5 plus 5/5, so y equals 6/5. So my point of discontinuity is at 1/5 and 6/5. So my domain is x such that x cannot equal 1/5, but it equals everything else, so XER. And then my range is y such that y cannot equal 6/5, but it's everything else. YER. Okay. If I went to draw the graph, I would draw the graph of x plus 1, but I would have an open dot at 1/5 and 6/5. So when I go to draw this graph, I go plus 1, which is my y-intercept, and then I go up 1 over 1. And I can go in the other direction, down 1, left 1. And then I have a line like this. But what am I forgetting? Point of discontinuity. So at 1/5 and 6/5, I actually have an open dot. So you would erase it away. I can't erase it because I'll lose so much stuff. But this blue line should not be passing through it. Okay? You would erase the blue line at 1/5 and 6/5. You would erase that blue line and put an open dot. Don't have the line still going through it. I just can't erase it or I'll lose so much stuff because my eraser's huge. You want to make it tiny, it's still big. So how could we check ourselves? We don't type in this equation. We type in the original equation, and you should get this. So let's see. You're going to help me because I don't know what it is. Alpha y equals, enter, what was it again? Oops, so 5x squared plus 4x over 5x minus 1. Graph. Zoom 6. Stop. Zoom 6. Zoom 6. So it looks like a straight line, and if you forget about the point of discontinuity, you're not even going to see it. But I can check myself. I can go second trace value 1 divided by 6. That's not true. 1 divided by 5. And I don't have a y. Second trace value. Second trace. because it's a terminating decimal. Because it's a terminating decimal. If you had like a decimal that kept going and you rounded it, yeah, absolutely you'd be wrong.
Or if you wrote out the whole thing.
And you will never write out the whole decimal because it's just, it maxed out at your screen, but it keeps going. Yeah. Okay, what about this one? So these ones, the numerator is bigger than the denominator and one thing cancels off and I'm left with a line, correct? What happens if my numerator is the same degree as my denominator, but they're both x squareds? So, let's try this one. Y equals x squared plus 4x over x squared plus 9x plus 20. Try it out. So this one is a GCF of x. You're left with x plus 4. This one you get x plus 5, x plus 4. Okay, so the x plus 4s cancel, just like they did factors canceled before, right? So now my reduced equation is y equals x over x plus 5. The last one, my reduced equation was a line. So I drew the line and then I put an open dot in it, correct? This one, my reduced equation is a rational. So I'm going to draw a rational with an open dot. So I know that x cannot equal -4, right? I also know x cannot equal -5 because those are my non-permissible values. We agree? But we're just going to deal with the point of discontinuity right now. So the point of discontinuity is at -4, comma, I don't know, let's see. Y equals -4 over -4 plus 5, which is -4. Oh, boom, we have an invariant point if it was an inverse graph too, which it's not. I just wanted to bring that back up. Because if we flip them, they'd stay the same. But anyways, -4 is our point of discontinuity. Yes? The last time, I just went to this lovely little ditty here, and I drew it, and then put an open dot in it, didn't I? This time, I'm going to go to this lovely little ditty, and I'm going to draw it and put an open dot at -4, -4. But that lovely little ditty is no longer a linear line. It is actually a rational. So we have to use our rational rules. So not only do we have a point of discontinuity, but because we still have a denominator, we actually have a vertical asymptote. It's at the other non-permissible value. So we have a vertical asymptote. So we use our other rules. We have a vertical asymptote at what? X equals -5. This is stuff we learned yesterday. And then we can use our rules. Because the numerator is the same degree as the denominator, what's our horizontal asymptotes at? Nope. Yeah, because it's the same degree, we take a fraction of the leading coefficients. So our horizontal asymptote is at y equals 1. So we're going to draw those first. 4 canceled. If a factor cancels, it can't be a vertical asymptote. It's point of discontinuity. So I always do those first, deal with points of discontinuity first, then deal with the actual graph last. Because -x plus 5 did not cancel. In order to cancel, in order to be a point of discontinuity, factors have to cross off top and bottom. Because they go away, but actually there's still a hole left where they were. They leave little reminders, you know. So we're going to type in the original always. So I'm going to type in alpha y equals enter. I'm going to type in x squared plus 4x divided by x squared plus 9x plus 20. I know right off the bat to draw this graph, I can put my asymptotes at the very least. So I can do the 3 things I know I have. I have a horizontal asymptote at y equals 1. It's my phone. It has a TI-83, TI-84 calculator on it. Because I'm running with an Android, and you get this for free. And then there's all you little iPhone-y people. You don't get this, not even for buying. I can, but then I'd have to reinstall. I'd like delete it and reinstall it. I'm not doing that right now. Yeah, it's my phone.
Why do I pay $8?
Well, first off, if you had access to your phone on a test, you could do a heck of a lot more than just use this calculator. And your calculator's a heck of a lot more than $80. It's at least $130, $140. Yeah. Because that's where your non-permissible value is. If I put a -5 in, my denominator becomes 0, and I have problems. The vertical asymptotes are always where the non-permissible values are if the factor didn't cancel. So then, at -5, I have a vertical asymptote because my denominator. So I draw those two things. I have another thing I'm going to draw. -4 and -4. What's there? Your point of discontinuity. I can't say it wrong anymore. People who are watching this are going to think that's what it actually is. -4 and -4. I have an open dot. So the graph's going to cross through there somewhere. Now, how do I get the rest of the graph? I go second table, and I pull values off of it. Now, what I could also do, you guys, I could also go this. You guys could go second trace value and plug in the x values. It'll give you the y for each. So if I want to draw on this side, I know I need lower than -5, right? So I'm going to do -6. So I'm going to go second trace value, -6. Everyone try it along. If I want to pick values off of it, I can go second trace value, -6. Second trace value, it pops up x equals, and then I can type in -6 and it'll give me the y. Oh, it's 6. So I'm going to draw it. 1, 2, 3, 4, 5, 6. It's number 1. And then I'm going to go second trace value, -7. I could go to my table of values, but if I want any other decimals in between, say I wanted to find between -6 and -7, I could go second trace value, -6.5, and it would give me the y value, and I would plot it. So it's at 3.5. And then I'm going to go second trace value, -8. And I'm going to get 8 over 3. Why are these in fractions? I wish they weren't in fractions.
Yeah, they're all in fractions.
You can turn them out into decimals too, but.
I like how the colors fit you through the graph. Even a little bit wrong on the diploma.
Yep. Needs to be accurate. No, you need to draw it.
Oh no, they'll give us a graph. Yeah, no, they'll give us a graph.
Yeah. So you have something like this, right? And then I would go second trace, -4. Oh, it's going to error me. Why?
Oh wait,
That's my point of discontinuity. So if I just use -4, I can't get anything on the left of it. So I'm going to go second trace value, -4.5, because I can't use -5. So -4.5 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. -4.5 and 9. So it's cutting along like this. Then I use second trace, -3. Value, -3. And 1.5. 1.5. -1.5. And then second trace value, -2, is 2/3, -2/3. And second trace value, -1, is -1/4. Second trace value 0 is 0. So, do you get the point? And then you would draw as many points as you could, correct? Do you see how I didn't draw a line through it this time? Through the you can't, or else you've just connected it. You made it continuous and not continuous. It's just a bit of a debacle. Okay? So the last ones we did, the ones before, when it canceled off, I was just left with a line, and then I just put my point discontinuity in the line, right? This one, I'm left with actually a rational, which I have to state the vertical and horizontal asymptotes to, and draw the point of discontinuity, which I draw first. Okay? So you're going to try this. They're just x cannot equal. Sure. We'll go, this is a good idea, because there's two of them. Domain is going to be x such that x cannot equal, what are my two x's it can't equal? Yeah, -5 and -4. And to be honest, when I give this on a test, you guys will forget the point of discontinuity. You'll state it can't equal the asymptotes, but you'll forget the point of discontinuity, or you'll state at the point of discontinuity and then you won't state the asymptotes. And then the range is y such that y cannot equal -4 and 1. -4 is the point of discontinuity, y. Because the point of discontinuity also gives you a y that doesn't exist. So this one I want you to get the points of discontinuity and the asymptotes, and I want you to sketch it, and I want domain and range. Go. If I factor the top, I get 2x squared plus 7x minus 15. I get 2x squared plus 2x, plus 10x minus 3x minus 15. Take a 2x out, I'm left with x plus 5. Take a -3 out, I'm left with x plus 5. And so I get 2x minus 3, x plus 5. That helps me with my denominator. 2x minus 3, x plus 5. If I do my denominator in the form it is right now, I'd get 3 minus 2x, 3 plus 2x, but I need 2x minus 3, 2x plus 3. So if I take a -1 out, then I can go 4x squared minus 9 and get the proper order. So I'm going to get 2x minus 3, x plus 5, -1, 2x minus 3, 2x plus 3. So these ones cancel, and when those cancel, I get a point of discontinuity there. So 2x minus 3 equals 0, 2x equals 3, x equals 3 halves. So I'm going to get a point of discontinuity. What's left over is x plus 5 over 2x plus 3, which is irrational, right? Not sure why I'm putting in brackets. You're welcome. Okay, so I have 3 over 2, and then I need to find my y by plugging it in there. So I'm going to go y equals 3 over 2 plus 5 over 2 times 3 over 2 plus 3. So I'm going to get 10, 13, really? 13 over 2 over 6. 13 over 12? What is it? 13 over 12? Shouldn't be negative. It's 13 over 12. They're all plus. How is it negative? Should be 13 over 12. 3 over 2 plus 10 over 2 is 13 over 2 divided by 6. Oh, there is a -1. Praise Jesus. Look at you for remembering that. Good on you. Yeah. So it's 13 over -12 or -13 over 12. Thank you. That would have been really awful without that -1. Then, super big error. Could have been super big. Okay, so now we have left y equals x plus 5. Once again, not sure why I put in brackets. Minus 1 over 2x plus 3. So my only NPV that's left is 2x plus 3 equals 0. 2x equals -3. X equals -3 over 2. It didn't cancel, so it's not a point of discontinuity. It's a what? A vertical asymptote. And they're the same degree left. So it's going to be 1 and -2. You put the negative through. So you'd go x plus 5 over -2x minus 3, because I need to have the coefficients, right? And you catch yourself because you type the original in and see that it's a negative, not a positive. So we have a horizontal asymptote at y equals -1/2. And then if I stayed in my domain and range, my domain would be x such that x cannot equal plus or minus 3/2 because of the point of discontinuity and the asymptote. Why am I putting a y? And the range would be y such that y cannot equal -1/2. Most people remember that one, but they forget the y to the point of discontinuity, which is -13/12. Why, yeah. Your homework is page 451. And remember, type the original always in if you're checking it, not your reduced form. You'll miss the point of discontinuity. Page 451, number 2, and then 4 to 6. 5 and 6 are just matching.